Okay, hello. Good morning, good afternoon, good evening. Thank you for joining us for the third talk in this series on the networking channel. Just waiting for the attendees to enter the room, and we should be getting started in the next few seconds. Just waiting to reach a quorum. Great. So I guess, yeah, in the interest of time, we should just get started. So once again, hello and welcome. I'm Manu Gosain, Senior Technical Program Director for the NSF PAWR program here at Northeastern University. I'll be sort of just emceeing and moderating the panel and doing the introductions for the panelists. Very excited on this particular topic, just personally, having been a researcher in this field, and really excited to have the panelists join, sort of representing different viewpoints. Just to set the tone for those of you who haven't been participating in this networking channel series of talks and panels, we are taking lots of different topical themes. And in this case, we're talking about 5G and next G innovation opportunities and challenges. This is going to be a much more of a macro view, primarily looking at an entire end-to-end network architecture from the radio access network, edge, core, service management, orchestration, and all the enabling technologies over the past few years. This is not going to be pedagogical in nature. So essentially, this is not talking about how we got here, but primarily looking at what are the opportunities, challenges for researchers, both in industry and academia, to be able to really understand and absorb what are the main challenges that still need to be solved, what are the main opportunities, and for our federal agency stakeholders and our funding agencies, for them to understand what sort of programs will spur innovation in this area. So having said that, I just want to move on to introduce our panelists. The panel will be kicked off and led by Dr. Guru Parulkar, who's the Executive Director of Open Networking Foundation and ON Lab. He's also the Executive Director of Stanford Platform Lab. And if you have been in this field, you obviously know this field sort of is synonymous with Dr. Parulkar. He's been in this field for over 25 years. So he'll be leading us off. Then we have Dr. Sachin Katti, who's a professor at Stanford University and also the co-chair of the ORAN Alliance. And this is going to be very exciting to sort of hear from him, because he's straddling both worlds in industry and academia, and really gives us a very solid idea of where the ORAN Alliance, which is led by industry stalwarts, is actually moving in this arena of 5G and OpenRun. Moving on, we have Florian Kaltenberger from EURECOM. He's a professor there, but also is a strategic member and one of the main technical leads for the OpenAir Interface Software Alliance, where they've been developing end-to-end 5G software-defined protocol stacks. And he'll sort of talk about more of the radio access network piece, functional splits, disaggregation, and what are the main sort of technical challenges there. Then Christian Maciocco from Intel brings in the industry perspective and basically will give us an actual pragmatic end-to-end network architecture example that takes us into a much deeper dive of how a 5G network that is enabled by disaggregation, software-defined networking techniques, and softwareization in general can be executed. And if you are somebody who's looking to do research in this field or already doing research in the field, this is sort of the sort of gold standard or reference design that we believe the community should adopt, and we should move forward with that. So with that, I'd like to pass it over to Dr. Parulkar. Just two logistic words. Question and answers will be handled both on the Zoom chat feature. So if you have Q&A, please use the question and answer feature on the Zoom. We also have a Slack channel, ACM SIGCOM Slack channel, where we'll be monitoring for question and answers and discussions. At the end of this, the recordings will be made live and available, and the slides will also be made available on the website. And we will also release a kind of a post-analysis of the main topical themes that were discussed here in the form of a newsletter at the end. So with that, I'd like to pass it over to Dr. Parulkar for some opening remarks. Over to you, Guru.
Hi, Manu. Thank you so much. Really appreciate the introduction. And hello, everyone. It's a real pleasure to have this opportunity to participate on this panel and share our thoughts on this exciting topic, 5G and next G innovation opportunities and challenges that are specially enabled by disaggregation, SDN, and open source. Let me start with an observation that I believe we are all familiar with already. If you're, I'm pretty sure all of you are paying attention to this, and that is 5G combined with IoT and HCloud will have a transformative impact on our society and on our industry. And this is where major infrastructure build out is going to happen over the next 5 to 10 years. And that is, and if you don't believe me, you can even look at some of the leaders of the biggest public cloud providers, what they are talking about 5G and edge cloud and the opportunities in this context. And they are making significant investment and they are pursuing this opportunity, a transformative opportunity. But my punchline is that we as researchers have a big opportunity to shape this transformation. And that is exactly, and this is, if nothing else, hopefully you will take away with this, that there is a big opportunity for researchers to transform and to shape this transformation. And again, this is enabled by disaggregation, SDN, and open source. Let me try to explain what I mean by disaggregation, SDN, and open source. And rest of the speakers, especially Sachin, Florian, and Christian, will take you into more details. But one meta observation I want to make is that until recently, until maybe 4G or even early days of 5G, we used to build mobile cellular networks using two big subsystems, and they were closed, vertically integrated, and proprietary. The radio access network realized with eNode Bs, and then mobile core realized with SNP gateways and the associated control plane. Now, thanks to the work of Sachin and a lot of other people, what has happened in last 10 years is this whole thing is getting disaggregated, software defined, and virtualized. I will not go into the details of it because I know Sachin and others are going to talk about it. But interestingly now, if we look at how people are trying to build 5G and next G, the architecture looks something like this, which is nicely disaggregated into forwarding plane and control plane, and everything is getting software defined. And as a result, there is a lot of opportunity for us to participate and contribute and shape it. Even more importantly, because there are many open source platforms are emerging for the research community to use and build on. So this combination of disaggregation, software defined, combined with availability of open source platforms are creating unprecedented opportunity for researchers to shape the next most important infrastructure of our industry for our society. And hopefully that is what you will all walk away with. If you are already participating, then that is great. If you are not, let me try to take you through some specifics of how this can be done. Now, I'm going to talk to you about one example project that I'm personally involved in. It is called Pronto and Ether. It is funded by DARPA, where we have a collaboration between among Stanford University, Cornell, Princeton, and this Open Networking Foundation. So Open Networking Foundation is responsible for actually building open source 5G connected edge cloud platform and an infrastructure with the community. And then we are working with the universities to allow them to do some very exciting and forward-looking research on this platform that has to do with network visibility, verifiable infrastructure, and network verification, and closed loop control to deal with security problems, to deal with congestion, deal with network failures and all of that using a very tight closed loop control. So this is an example project. Now, this is currently, this is what it looks like. That is, there is a cluster of servers. This is the edge cloud, our version of edge cloud with a servers and SDN fabric. Right now we are using a 4G. Very soon we will replace that with a 5G radio, which is ORAN compliant, a number of IoT devices, including drones, and then of course, a number of smartphones that are connected to this. It is already deployed. in close to 15 locations where people are using it for research, experimentation, and all of that. And this is deployed around the globe. And we are operating it as a kind of a pilot network. Okay. Now, what is interesting is, as a researcher, you have an opportunity to play with this, and you can play with this at multiple levels. You can take a narrowly focused problem, and because it is all software defined, disaggregated, and open source, you can work on a narrowly defined problem, bring it into this infrastructure, experiment with it, and all of that. You can work on something big. If you don't like our implementation of some big function, you can replace it with your version of it, and you can work with that as well. Okay, this is a 3GPP and ORAN compliant. So that means whatever work you do, it is relevant to the industry and it can be adopted in real world. Also, because it is kind of production ready, it is operational. Whatever work you do and put into the context of this, it can be used immediately in a kind of a pre-production setting with real traffic and real user. So this is the example of something you can use, and you can impact the future of 5G and next G at whatever level you decide to choose. So that is the opportunity that we are trying to outline here. Now, what I want to outline is that, as Manu said, I have been in the field for close to 30 years. So I started my graduate school in 1980s. That was the beginning of the internet. And I find a lot of similarities in what happened in 1980s and how the research community shaped the evolution of internet and the opportunity that is coming together for shaping the future of 5G and next G in this. So let me walk you through some examples. So 1983 is when ARPANET adopted TCP/IP as a standard. There was only 1 or 2 implementation, and ARPANET said, okay, this is the protocol standard they are going to use. In 1980s, DARPA funded a big project at UC Berkeley to develop open source BSD with the TCP/IP stack. Majority of the TCP/IP stacks used after that have been the derivatives of this TCP/IP stack that was built at Berkeley. Okay, the socket interface and all of that came out of that work. In 86, NSF funded NSFNet, but more importantly, what NSF did during 1980s and 90s is something that was called infrastructure grants. They allowed every university or most of the universities to acquire Ethernet, a VAX, typically a VAX, and a set of workstation, and allowed them to build their own campus network, typically in computer science or electrical engineering department. And then the computer science community, including myself and many people that are very, I mean, not me, but many other people that are very famous, they did their PhD research on this network and with NSFNet. Okay, and you can see that between 1985 to 93, number of hosts, connected hosts, grew from 2,000 to 2 million plus. Okay, and that is the beginning of the commercialization of internet, and then the rest of the, as they say, is the history. But what is important is during that time, it is the research community that impacted the evolution of internet and made a tremendous impact on the evolution of internet. Now, if you look at the 2020s, you will see something very similar. That is, 5G and ORAN architecture and spec are now relatively mature. DARPA has been taking the lead in funding disaggregated software-defined open source 5G. NSF is funding some shared facility. So I believe it is time for funding agency, hopefully NSF, to allow many CS&E departments and campus IT to acquire private 5G HCloud infrastructure, so that all these universities can do research on their local context and be able to innovate with 5G and all that. So my only ask is, if you are listening to this particular webinar and this particular session, are you ready to ask your funding agencies to get you your own open source private 5G with connected HCloud so you can shape this transformation? I hope your answer is yes, and that is what you will ask for and how shape the future of 5G and next G. Okay, with that, I want to pass it on to Sachin, who is going to tell us more about ORAN.
Thank you, Guru. Can you see my screen?
Yes.
All right, thank you. So that was a great introduction, and I think it already set the stage for why we need to be able to focusing on disaggregating and opening up this infrastructure. So let me tell a little bit of background. So I see many names on the attendee list. Many of them are familiar to me. You all work in wireless research and specifically cross-layer wireless research, right? And I did a lot of work in the space, full duplex, network coding, coexistence, so on. And one of the frustrating things a few years back for me was that the impact was quite limited on what was actually happening in the industry, right? So one of the knocks on wireless systems research was, it's great, it is on Wi-Fi. We wrote a bunch of very interesting papers, but it really hadn't changed the way mobile connectivity was delivered to most of the people in the world, which is obviously 4G and now 5G cellular networks. So what we kind of really set out to do at that time was figure out how can we actually make it possible for innovative academic research like this to be able to transfer to practice without the enormous burden of building something, prototyping something that actually implements the entire architecture. It's extremely hard for a small research team to do that. So how do we transform these deployed cellular networks to be more open to innovation? And that's the story behind ORAN actually. So we founded what was called then an XRAN forum in 2016 with a few operators that were interested in pushing this, AT&T, T-Mobile, and SK Telecom. And there were a bunch of smaller network equipment vendors. None of the big vendors participated initially, right? So this was just how do we build such a architecture and a platform and transform as 4G becomes 5G. And XRAN became ORAN Alliance in 2018. That's the term you hear about quite a bit. It's now basically a global body, which I chair. It has pretty much every operator in the world and every network vendor in the world that is now participating in this and working together on defining this next generation architecture. So that is the story. And I think it very much mimics what happened with data center Ethernet networks and enterprise networks with SDN. So the same transformation that SDN brought about to the wired world, how do we bring that about to the cellular wireless world? So that's kind of really the focus of what ORAN is trying to accomplish. So now, where are we in this journey, right? So one of the things that has pleasantly surprised me is that it's actually already taken off very quickly. So for the cellular world, anything happening in 4 years is like a blink of an eye, right? It doesn't happen that quickly. And we already have several commercial deployments that are now beginning to roll out an ORAN architecture, right? So Dish is going to be an example here in the US, where they're going to be rolling out a US-wide 5G network standalone that is going to be fully ORAN compliant and is going to have all of the capabilities that I'll talk about in a minute. But Rakuten did it in Japan a couple of years ago, and then now they are transforming it into a 5G network. And a lot of bigger, more conservative operators, right? So Verizon, Telefonica, Vodafone, a bunch of them around the world are now beginning to kind of deploy an ORAN compliant network as they start rolling out 5G. This has obviously also come up in the geopolitical context. And I think for the US at least, this has, and even Europe, this has been an opportunity to kind of really open up this infrastructure and enable a much newer crop of vendors to enter the market, which had consolidated into 2 or 3 vendors around the world, which had stifled innovation, in my opinion. So what's going on, right? So that's kind of the market context. So what's really happening? What are we trying to accomplish, right? So this is a very stylized view of what the current cellular network looks like. And I'll take a minute to actually go through this in a bit more detail because I think it's quite illuminating. So you have what's called the UE, that's your cell phone, that's your device, user equipment. And then the infrastructure really starts from the antenna, right? So this is the stuff sitting at the top of the cell tower. Beneath it is basically the radio access network, right? That's what you think of as a cellular network, but it actually has multiple components. One is the radio unit, right? So this is the thing doing the signal processing in an FPGA, doing the down conversion from an analog to a digital signal, and vice versa. All of those radio magic, if you will. This is typically sitting at the bottom of a cell tower, right? And it's connected to the antenna. And then you have what's called the baseband unit. So this is what we think of as software-defined radio typically, right? So this is the base station software. So this implements the layer 1 to layer 6, layer 7 stack. And in 5G, this actually has two components called the DU and the CU. The DU stands for the distributed unit and the CU stands for the centralized unit, right? But basically they are different, they are two different components implementing together they're implementing the layer 1 to layer 7 stack that you'd expect out of a base station. And then you have a management plane, a management software that's actually in charge of managing all of this infrastructure, right? So in the radio cellular network, many of you will be aware, you have to manage interference, you have to manage mobility, you have to load balance across all of the different spectrum bands, all of the typical interesting problems we have tried to solve using these cross-layer techniques. That's really what's being implemented via this management plane. Right? Now, what is the problem with this picture is that this entire box, the radio unit, baseband unit, management unit, comes vertically integrated from one vendor, right? And so, by the way, the CN is the core network, right? So that's the packet processing. So what I'm focused really is on the radio access network. So because it came from one vendor, right? If you had an innovation that, let's say, introduced a new load balancing algorithm or a new way to do MIMO communication or whatever, it was next to impossible to get it into the market without convincing one of these big three vendors to actually open up their infrastructure and allow you to put your algorithm into it. Right? So it really increased the barrier to entry for a lot of people to be able to innovate and introduce their innovation in a scalable manner and essentially locked out both academia as well as startups out of innovation in this space. So what's ORAN trying to do is essentially try and really build a modular architecture that kind of disaggregates and unbundles this whole stack, right? So what does that component look like? So first of all, there is the radio unit, right? This was the one that is doing the radio processing. I'm calling it the RRU here, right? This is the remote radio unit. And essentially standardizing and defining a front haul interface, as it's called, between the radio unit and the DU, which is the baseband unit here, right? Now, this sounds trivial. It's like, okay, bits on a wire, who cares, right? So why is this so important? It turns out to be quite important from a commercial perspective because the RU, the radio hardware, is around 60% of the entire spend of a carrier for deploying a radio network, right? So it's extremely expensive. And for a lot of us wireless researchers, I worked on full duplex, so I built circuits that would go in an RU, for example. We tend to focus in this particular community a lot on software, but the radio unit is also where there's a lot of innovation in academia, right? People are building mixed signal circuitry, RF circuitry. They could not get their innovation into the market because the RU was tightly coupled with the baseband unit. Now, because ORAN has shown up and produced an open frontal interface, we actually see a lot of startups emerging that are only selling a radio unit now and commercializing innovation from Bell Labs and other universities. So there's actually, for the first time in 3 decades, a lot of interest in innovation in radio hardware that's showing up because it's now possible to be a standalone RU vendor and actually sell it to a big operator. And it has a huge business impact, right? So because it's 60% of the spend of an operator. Then between the DU and the CU is kind of the data plane. So to use Guru's language, so the DU and the CU are kind of doing the data plane processing. So they're processing the analog signals, the digital samples, and the bits, right? So by data plane in radio, I would subsume all three. So they're doing the heavy lifting. What we are trying to do is define programmability to that data plane via these southbound interfaces to a control plane, right? So very similar to what SDN tried to do. What is that control plane? How do I abstract the logic and the intelligence of actually doing radio optimization and network optimization via these southbound interfaces and allow you to program the network with real-time kind of control plane functions, right? So think of this as control loops that are trying to do things like if Guru's device is connecting to the AT&T cellular network and Guru is a high priority user for AT&T, maybe I should handle the admission control for that particular user differently than maybe, let's say, an IoT device, right? So again, these things sound trivial in the wired context, but this has been impossible to do in the wireless world, right? They have a one-size-fits-all policy. How do I actually get per user, per application programmability into the network? That's something that the control functions are trying to enable. And then finally, define again open interfaces for the operational management layer to be able to kind of manage, configure, set policies, define security, do slicing, all of these applications that Guru was mentioning, again, via standardized northbound interfaces. So the intent is that every box here that you see that is not an interface could potentially come from a different component, from a different vendor or academia, and could be programmed to actually allow you to kind of innovate in each layer separately. So really bring modularity to the architecture. So one example I'll focus on because again, it's a favorite topic of mine. It's close and dear to heart is the cross-layer wireless research, is this RAN control plane. And Guru mentioned this earlier, right? This platform that he was talking about is actually implementing an open source version of this control plane that will allow people to innovate. Once again, as I said, previously the data plane or the user plane, as it's called in the cellular network, and the control plane and the applications were tightly coupled, right? So you would have cellular telephony, which is the application, the control plane for cellular telephony, which is kind of how it's setting up voice circuits or voice flows, and the data plane all coming from the same vendor. So vertically integrated, you could not do anything different. What we are trying to do here is have that RAN controller, and the ONF is building an open source version of this RAN controller called the near real-time RIC, right? And having standardized interfaces to be able to program this underlying network. Now, what are the kinds of things it enables using such kind of interfaces, right? So it's kind of, here's a few examples I've seen around different companies and academia trying to do this, right? So things like our favorite research topics in the wireless community, right? So doing massive MIMO, doing kind of bitrate selection, that's called MCS selection, doing better pre-coding or load balancing. So those are kind of the XApps that are on the radio resource management side. But let me take the other extreme, which is we have literally written hundreds to thousands of papers on location, right? Localization. So this will actually enable you the interfaces to deploy your favorite new localization algorithm on a running network and see how well it works actually on a practical network rather than a testbed. And because localization is just a passive XApp, it's actually very easy for an operator to try this out because it's not like it's interfering with their production traffic. There's new capabilities coming that want to do true cross-layer, right? That want to take application layer context. For example, this Zoom session, if it is running on a cellular network, can Zoom program the underlying cellular network to be able to steer its traffic such that it gets a better quality of service, for example. So there's a whole host of opportunities coming where truly this cross-layer and radio network optimization capabilities that we've been working on can now actually be deployed on real networks and tried out. And this is where, for example, Dish is going to go in the US, where they're actually going to open up such an ecosystem via the cloud and allow people to experiment with their network and bring in new XApps. So really the goal is to get to an app store-like model for the network where anyone can build an app and the network operator can potentially consume that app and bring innovation into the network infrastructure. So I'll conclude here. In general, I think for the academic community, the big message I have is there's two places where there's a lot of room for innovation. So one is for people working in wireless hardware, really look at the radio unit now. And because of massive MIMO, because of mid-band spectrum, because of high-band spectrum, there's a lot of need for new innovation in radio hardware. So, and it's now possible to actually have an impact in practice because of those open interfaces there. And because of the decoupled control plane, there is now a big room for people working on cross-layer wireless algorithms to be able to actually deploy and figure out how well these things work in practice rather than use small Wi-Fi testbeds, right? So that's the other big opportunity. Larger message really is that what ORAN is trying to do, and we're still going to be, this is still a journey in progress, even though it has had a lot of momentum over the next few years, is to really get to that modular architecture, software-defined architecture for the radio network, which had historically been considered this hardware black box that no one could touch, and foster a lot of competition and innovation in this whole space. So with that, I'll stop and I'll take questions whenever they show up.
Thanks, Sachin. Over to you, Florian.
Okay, so I guess we're taking questions at the end, right?
Yes, that's right.
Okay. Okay, let me share my screen as well. Thanks, Sachin, for that presentation. That's a perfect, it's perfectly timed before my presentation because I'll make reference to this. Let me share my And yeah, as you can see, I've named my little presentation here, OpenRun and OpenAir Interface, the perfect couple, because I think there are a lot of things these two initiatives have in common, in fact, I think both of them together make make some powerful tools that are especially useful for the research community, but also for industry. So yeah, for those of you who are not familiar with OpenAir Interface, OpenAir Interface is a fully software-defined 3GPP compliant radio access network that works together with software-defined radios, like for example the USRPs, but also others. The project has been around for a while now. And it has become popular at around 2009 when we actually became compliant to 4G LTE. We can also do now today we can do 5G NSA already since last year, actually we are quite in the hot phase about releasing the 5G standalone. I think we're really just a few days, maximum a week away from having that ready. Well, actually, OpenAir Interface doesn't only provide the radio access network; it also provides an implementation of the core network, both 4G and 5G. So actually, with OpenAir Interface, you can build your own radio. Your own network, completely compliant with 3GPP. So, you know, you take a bunch of computers, some USRPs, and you take a commercial phone, and you have your own 3GPP compliant network. So that's and one of the key differentiators of this project with respect to others is that it's open source, but not only open source, it has an open source friendly license. So friend is the fair, reasonably and non-discriminatory clause that is used by 3GPP to share different patents. And basically this license that we introduced is one of its kind to allow companies that have portfolios in 3GPP to go and contribute code to this open source project without losing their rights to the patent. And it's a truly collaborative project. So we have I'm talking about the 5G development now. Has more than 20 contributors from over 10 organizations. And some of these organizations are listed here. So we've also created this so-called Open Interface Software Alliance, so which is an organization that that allows to collect donations, and with these donations we fund several activities to support OpenAir Interface. We also have in place now a big team of developers, engineers to handle the continuous integration, and yeah, it's an organization that everyone can join. So if you are an academic entity or a non-profit entity, you can even join for free. And so coming back to the title of my presentation, OpenAir Interface and OpenRun is the perfect couple, because OpenAir Interface actually gives you the tools to implement an OpenRun compliant network. So here on the left you see a similar figure that Sachin has shown, where with the well, a subset of it actually, with the different elements in an OpenRun network. You have the CU, centralized unit, distributed unit, and the remote radio unit. And today we do support all this interfaces, or we're just about to release them. So the F1 interface is almost ready. The F1C has even been tested with a commercial CU. The F1U is also ready and will be released very soon. We have and we also have the OpenRun 7.2 frontal interface that allows you to connect the DU to different radio heads. So in fact, today we do support commercial radio heads. So there's one example here from a company called Benetel in Ireland. But we're also planning to support different remote radio heads very soon. So there's an activity to extend the current implementation also to the other to the control plane and others. There's also quite a bit of activity and there are parallel activities as well in ONF to provide a completely compliant E2 interface. So that's the E2 interface. It's not on this picture here, but it's the one that links both CU and DU to this RAN intelligent controller, which then will allow people to also play around and develop X apps to control certain elements in the radio. All right, and to maybe finish off, I have some research topics that I think are quite hot and that are interesting to address. So I think I mean, Massive Mimo has now been around for a while, and most of the big vendors, I mean, they support Massive Mimo in one way or the other. But I think the full potential of Massive Mimo is not exploited yet. And I think OpenRun the OpenRun architecture is a perfect opportunity to do even more. So there's several sub items here. So one of them, I mean, that's a personal research topic for me, is pre-coding. This frontal interface allows several types of pre-coding, and I think it's a perfect opportunity to play around with different methods and exploiting channel that exploit channel reciprocity. I mean, the implementations you find today are usually based on a grid of beams with fixed beams, and it has been shown that in theory channel reciprocity provides the best performance. And I think this is more feasible to do in an OpenRun setting than otherwise. But there's also another aspect, and I'm putting this also in the Massive Mimo category, which is beamforming, which is a technique which is necessary in millimeter wave, but a technique which has its drawbacks as well, because it's hard to provide a reliable coverage with beamforming, because you need to track your users and you need to always make sure that you provide your user with the best beam. And I think here we can really benefit from this RAN intelligent controller and put some real intelligence in there, and even exploit some artificial intelligence in there to intelligently control these beams, especially when you have a multi-cell scenario and you want to coordinate beams between different cells. And I think this can be especially powerful in an industry 4.0 setting, which is a very hot topic. So combined with ultra reliable low latency and millimeter wave spectrum. And yeah, another hot topic, I think that is especially suited to this OpenRun settings is joint communication and sensing, which is basically using the existing radio signals that you have in your cellular network to get some information about your environment, similar to radar sensing, but using the existing signals. So this will allow the radio network to make some sense of its environment, and this information can then be used again in the rig to improve the overall network performance. All right, so this is what I've prepared.
Thanks,
Florian.
Florian.
Over to Christian.
Yep.
Okay, thank you. Let me share my slide. You guys see my slide right now?
Yes. Yes.
Okay. Well, first, thank you, Manu, for the opportunity to present here the networking channel. I'll be talking about Ether, which is an end-to-end 5G private network built on open source, disaggregated component, and using network function virtualization to really show how to build this network. Right? Let me show you what has been, a path of evolution from a traditional cellular network. In the past, if you want a cellular network, they run on a monolithic, vertically integrated proprietary solution. Right? You need a hardware box. Usually, they're provisioned for peak traffic. If you need to scale, maybe your control plane or your data plane, you need to buy another box, right? So, and there were, single-purpose devices. And you pretty much have no access, as Sachin mentioned earlier, you cannot do anything with the box. So, and we've been working, a long time with ONF, probably over the last 6-7 years. Our first step was through SDN, disaggregation, and virtualization. How do we build a mobile core, right? And following the SDN and NFV, architecture principle, we disaggregated a 4G LTE mobile core, right? So it was the first transition of a cellular workload from a dedicated hardware device to a high-volume platform, high-volume server, where we could use, CPU improvement, better cores, better frequency, right? Software improvement, for example, also the DPDK, data plane development kit, to get, very high I/O throughput through the platform, as well as other CPU improvements such as SGX, Secure Enclave, to secure your VM, which might be working, in a cloud environment, right? And you might have an untrusted cloud, but you want to secure your software. And so this work led to what we call OMEC, which is a 4G LTE open mobile evolved core. And actually, OMEC is going to production deployment at Dutch Telecom, T-Mobile Poland, for fixed wireless services. And people can attest it's not easy to take an open source solution and move it into a production network. It requires a lot of collaboration with the community. We had a lot of help with Sprint initially. System integrators also jumped in, GS Lab, HCL, Infosys. But at the end of the day, you still have here an open source based software going into a production network. Now, the second step here of the transformation was, how do we go into a cloud native model for scalable, and disaggregated network? Right? And that's the work we are currently doing, or have been doing, since last year with partner. How do we take this 4G LTE mobile core, evolve it toward 5G, enabling, distributed edges, which in turn enable mobile edge computing, application running at the edge of the network, have the ability to scale this network, in a fairly easy fashion. And again, for us at Intel, use additional CPU features or platform enhancement. We describe them, as we move along the slide, mentioning here DDP, dynamic device personalization, application device queue, smart NIC, right? But also as we move forward, how do we add more and more disaggregated components? And as the previous speakers talked about, an ORAN-based software-defined radio. Okay? So this is the Ether network, and we'll go into some detail about what Ether is and what are the Ether components. But the overall goal here is to deliver, cloud native, disaggregated, SDN NAV-based reference implementation with ONF and the community partners, right? As I mentioned, some of these solutions are reaching production network deployment with Dutch Telecom, T-Mobile Poland. DARPA also, as mentioned by Guru, is sponsoring research with ONF, Stanford, Princeton, and Cornell to deploy and operate this Ether network. And we see that, as mentioned by all the previous speakers, right? If there is a specific area of the network you want to work with, having a disaggregated network, disaggregated component allows you to do this, right? A lot of this, is a software-based implementation. If you want to do some specific research, if you want to add capabilities to some of the components, the platform is open. Most of the component and the Apache v2 license, permissive license. So you have access to most of them, right? But let's take a look into what Ether is today and where Ether is going toward 5G network. So what is Ether? Well, there is a set of software developed by ONF, which you call Ether management, right? How do you install software on a platform? Let's say you get into an IT department, right? People are not familiar with a private network or cellular network. How do you install software on the platform? Bring up Linux, install Kubernetes, push the various containers where they need to be pushed, right? So we call all this part of Ether management, right? After, how do you control the services you're running? How do you monitor the services, and the operation, right? Dashboard and everything, right? And so they're using Rancher to push and set up the platform, right? To install all the software components. And here we have the Ether management as well as the mobile core control plane, both the 4G control plane as a 5G control plane, which is coming from Free 5GC, another open source project, running in a hyperscaler cloud. Here they're running in Google Cloud. They have run also previously into Azure, right? So this is the central location. Let's say you have a company, for example, like Intel. We could run this central control plane into a Folsom in California IT department and serve all Intel branches around the world with different edges, right? And similarly here, then you have the edge, right? And today on the 4G LTE edge, I saw someone earlier ask about, how do we get spectrum? Today we're using CBRS 4G radios, right? So it's free spectrum access. And we have the edges where we run part of the stack, right? We run the UPF in 5G's intermediary UPF, which will enable, allows you to run mobile edge application at the edge of the network right there, right? Connected to the radio. And then these edges are duplicated. Today there are about 16 edges. We have about 12 edges in various commercial companies, AT&T, NTT, Telefonica, Siena. ONF has about 4 or 5 edges in different locations. Intel also, has few edges running. And there are edges as part of the Ether DARPA Pronto project. Right? There are 2 edges at Stanford, 1 edge at Princeton and Cornell. Right? And so all these edges are managed from the central location, right? When your device joins the network, we have this hybrid cloud communicating through each other, right? From the edge to the central cloud. Session is being established, and then the data flows, right? Whether you have an application at the edge or you need to reach the internet, the session will flow across, right? And your device will connect to a cellular network. This cellular network is being monitored, constantly, right? And you have a ton of telemetry data. Telemetry data both at the platform level, right? CPU, memory, storage, network usage, right? What is the characteristic performance of the platform, as well as telemetry data at the 3GPP component level. Your MME, for example, right? How many attach, detach, timer update, the UPF, what type of latency do you see going through the UPF, and you can chart the latency information. Today, we are not yet taking specific actions, for example, of the latency in the UPF, But having the data available, we're working, and specifically talking for Intel, we have some capability called resource director technology, where we can assign shared resources of the CPU, which is a last level cache, memory bandwidth, IO bandwidth. We can assign specific resources to specific processes, specific VM or specific containers. Right? So in the case of the UPF, if we see some latency spike, the orchestrator could take some action and give us a little bit more shared resources to make sure we're meeting, our SLA. Right? So today, Ether basically it's this cloud native mobile core, which has the ability to scale up. Each component can scale up, and by this meaning based upon your traffic requirement, we add CPU core, for example, to the UPF. And I'll show it to the next slide, right? Or we can scale out. We create another instance of the container, and we scale out, this way. Now, today, ONF deploys and operates this network. They provide day zero, again, installation of the software and the component of the platform, day one and day two operation, both for this commercial site as well as for DARPA. And if you want to build such a network, the BOM cost is very, very low, right? You need to buy, one of these small cells, which is, few $1,000s, right? I know CBRS radio is probably around 2K. Then you need, one or two servers to run your edge software, right? And the rest, you rent VM or you rent space into an hyperscaler, cloud provider. Now, we're moving toward 5G. This is, a 4G LTE solution. And we're moving toward 5G, where you see with the same picture, but the radio here on the left, instead of being, a CBRS small cell, right, a box, we're moving to an ORAN based radio. So let's go to the next slide. Oh, sorry, yeah. Before going to the next slide, I was talking about scalability, for example, showing here the UPF, where we want to address various deployment models. Let's say you have servers at the edge, right? And you want to push a container. You use what you see here on the left side, which is basically an implementation on the host, it's a container. Instead, you want to aggregate a lot of traffic in the central office type of location, and you want very high throughput and your jitter. The UPF also is implemented on Tofino. So the UPF itself is disaggregated. It comes as a slow pass and a fast pass. The slow pass basically handles the PFCP communication and the session state, right? And the slow pass supports multiple fast pass, right? So there is an implementation on the left side where, again, you run on the host and you can do a full UPF implementation on the host, supporting hierarchical QoS, data downlink notification, some DPI. We use some CPU features or platform features. One of them is DDP, dynamic device personalization. And the chart below shows you with DDP, we can do a GTPU, basically load balancer in hardware on the NIC, right? So we load balance the GTPU traffic on the NIC, and we feed different cores. And here we see that, with 8 CPU cores, we achieve about 98 gigabit per second throughput with one NIC, right? So on the platform, with the latest generation Ice Lake platform, right, the third generation Xeon scalable CPU supporting PCIe 4, you can put 3 or 4 Columbia-ville, this 800 series NIC, and you get 300 to 400 gigabit throughput per platform, right? So you start to have significant data throughput on the platform. On the right hand side, the Tofino switch gives you up to 12 terabit worth of throughput. But to do a full implementation of the UPF, you will have to offload some of the functionality to an FPGA or to a CPU, the host CPU of the control plane of the Tofino, or any other host CPU to do hierarchical QoS, DDN, or support very large table, right? But again, we want to be able to support all type of deployment model. Having the pipeline defined as a P4 pipeline, I don't show a picture in the middle, but Intel also has an FPGA and we have a PFO to FPGA compiler. So you could take the PFO pipeline and run it on the PAC 3000 card, which is again a NIC plus an FPGA device. Right? So now, how do we move toward 5G? And by the way, the UPF is a dual mode UPF. It understands both 4G LTE as well as 5G network. So moving toward 5G, that's pretty much the same picture that we saw before, right? For the control plane, the edge software, but now the radio moved toward an ORAN-based radio, right? As mentioned by Sachin, and Florian earlier, you have the DU, we have the RU, DU, and CU breakout, right? In our first build-up here of the 5G edge, the RU come from a Foxconn. So again, you can here mix and match different vendors, right? The DU comes as two components, FlexRAN from Intel providing the DU low, interconnected with Radisys to provide the DU high as well as CU, right? So FlexRAN, if you want, provide the L1 layer, and Radisys provide the L2 and L3 layer here. Radisys also expose the E2 interface, which was talked about earlier, feeding the RIC, right? And on top of the RIC, a RIC defined by, developed by ONF here, based on micro ONOS, right? And ONOS with the Open Network Operating System, which has started to have a significant mileage and production deployment also with various people, like Comcast and some project also in Dutch Telecom. So the RIC enables XApp, and this is, an area rich for research and for experimentation, right? Today we have few XApp. There is an XApp from ONF doing load balancing. There was some machine learning AI-based XApp from Intel for optimizing connection management. There is an XApp from Facebook and Europe doing self-organizing network, right? Again, it's a space where people here will innovate, right? And as mentioned from yes,
sorry, just want to jump in the interest of time, and if we can, move to just a little bit of the. I love this sort of picture because this really summarizes and what everybody has sort of brought to bear in an end-to-end fashion. I think based on the themes of questions that we're getting, and thanks again to the panelists for answering them live, the whole. I guess we don't have that much time, but I'd be curious to get your sort of remarks, and we can go around the table, starting with Guru, would be the on-ramps, aka for somebody who's in an academic environment, trying to sort of get this started, right? So to set this infrastructure up, and there were some questions around that. We heard some answers, but where would one kind of start? Right? And then how would they be able to go around and test it? I think this is a beautiful picture here. It not only, it shows the complexity, but it also shows that solutions are available and they are sort of cloud native, software defined. But what would you say to that, that person who's looking at this particular area for experimentation, research purposes? What's the on-ramp, or what would be your guidance as to how to get started here? Maybe Guru, if you want to kick it off and, just.
Right. So I guess, as I mentioned, there are multiple open source platforms that are becoming available, and, one could decide based on the scope of work, which open source platform they want to focus on. In our context, say Ether, we are actively supporting universities to acquire a local Ether and using CBRS spectrum or that kind of experimental spectrum, they can deploy a 5G network. And as Christian mentioned, we support day 0, day 1, day 2 operation, and take the universities through this particular step to acquire it, get it going and all of that. And then in the context of Ether, they can choose which part of the component or research they want to focus on. I do want to mention that on one end, this is a huge opportunity, but there is a learning curve that cannot be denied. Some of these software systems are complex, and if you want your graduate students or postdocs to work on it, there is a learning curve and how to do development in the context of this complex software system. We at ONF are trying to help and make it easier, but there is no two ways about learning that. But the return on investment is very good, because this is the environment in which graduate students and postdocs are going to go and have to work and do software development. So we are trying to make it easier, and people can reach out to us. We will tell you what kind of infrastructure they can acquire and how we can help them, and other open source projects do the same thing to bring people up to speed on that.
Fantastic. Sachin, if I can get maybe a word from you on this topic, that'd be really good, and then we'll have to wrap up.
Sure. So yeah, I think as Guru said, I think there's two vehicles here, right? So one is operators like Dish and others are going to enable platforms via the cloud that will allow you to kind of experiment with real deployed networks. That's coming fairly soon. So that should make it easier to access. The other is, I would really encourage everyone, and Guru already alluded to this earlier, is to get funding from NSF, whoever, encourage your department's IT managers to deploy a private 5G network alongside your Wi-Fi network, right? So inside, for example, your building, and use this as we did like 10 years back with SDN and OpenFlow as both a production as well as a test network, because you have the capabilities to do so, and spectrum allocation policy is becoming easier to access also. There is no substitute for learning by doing, right? So I think that's really the only way we'll make progress here.
That is a fantastic way to end things here. I think that is the key, I guess, message to see. It is a complex topic. It is very fast moving, and there's lots and lots of challenges. But again, I think, Sachin, to borrow what you just said, learning by doing is the way to do it. So hopefully this sort of gave you a nice primer as to what all is going on, what's the state of the art in industry, where academia can participate. I know we're a couple of minutes over, but really want to thank, with virtual applause, I believe, our panelists for their time. There were some questions that are still open. We'll make sure that we get those answered for you. The recordings will be available on the website. And really, thank you for spending this hour to all the audience members from around the world. So thank you so much, and we'll see you in 2 weeks for the next topic. That's going to be looking at how to succeed in grad school. So for more details, please visit networkingchannel.eu. Thank you so much. Thanks, everyone.
Thank you, Manu.
Thank you.
Thank you.
Bye-bye.
Bye.
Bye-bye.
Thank you, Manu.